right, good afternoon, everyone. Welcome. We are really excited and pleased that you could join us here today for the School of Molecular Sciences annual fall welcome event. So my name is Chad Borges. I'm an associate professor in the School of Molecular Sciences, as well as the associate director for undergraduate programs in the school. So today I'd like to extend an especially warm welcome to our incoming freshmen, those of you who are our newest Sun Devil chemists and biochemists and who are a really important part of our School of Molecular Sciences community now, including those of you that are watching online. You're a really important part of our community as well. So as incoming chemistry and biochemistry majors, you all know what chemistry is all about, right? At least in a general sense. It's about atoms and molecules and all the which make up everything around us. It's about matter. So just everything you see, taste, touch, smell, it's all chemistry, including our own bodies. So, chemistry is all about what is it and how much is there. It's about how matter changes as it interacts with as the physical environment changes. It's about how one form of matter interacts with another form of matter to make change. And perhaps most importantly, molecular sciences is really all about how we can take this incredible body of knowledge that we've gathered over the past 100 years or so, even more than that, and apply it to our world today to make a positive impact going forward. So as chemistry and biochemistry majors, I think you know this, you're in for a lot of hard work as you study chemistry over the next 4 years, and really as you become lifelong learners about chemistry and biochemistry. But today, it's really about just having some fun with chemistry and biochemistry, and maybe learning a few things along the way. So we hope you'll enjoy the presentations that we've prepared for you. Before we get started, I want to introduce our esteemed director, Professor Tiana Rai.
Hello. As Chad said, I'm Tiana Rai, the Director of School of Molecular Sciences. First, I want to congratulate you for your acceptance to the School of Molecular Sciences. It's a great thing being part of this very warm community. So, what I want to tell you, we all here, as you're going to see later on today, enjoy chemistry and biochemistry, learning about it, seeing how atoms and molecules engage into chemical reactions and how they change the environment around them. So as a student here, you will be learning about the same things, how atoms and molecules will, for example, react to create drugs, how they will react to create our better environment, and how you can change this as you study and learn about the reactions, how we'll use that to make a useful contribution to our society. Most importantly, as a student here, you will be learning to think independently. This is something that's going to stay for you in your life, and it's going to help you find the job that you like, will help you think about the solutions that you can find. And also what you're going to learn here is to work with your colleagues and your teachers to achieve your goals. These are things that will help you engage in life in a more complex world that we are part of, and find the solutions for better environment and economy, and solutions for technological, renewable energy sources. All these things are actually with chemistry. So without further ado, I want to congratulate you once again and hope to see you soon.
All right. So to kick things off with our first demonstration, we have two of our esteemed academic advisors, Ruby Arjona and Sarah Johnson.
All right. And yeah, hello everyone. So we are just part of the academic advising team. I'm sure you will be speaking, seeing, emailing, Zooming with the rest of us as well at some point in time. But for today, we are going to try to start off with some magic. But we all know that matter is everywhere, right? It's in the air, it's in this water. If I pour the water here, You can hear it. It's in this bucket now, right? And there's lots of things you can do with matter. As we said, you can change things. You can, create new medicines. But Ruby, can we make matter disappear?
No, right?
That doesn't happen. Matter always has to be around. But
can we actually make matter disappear? It's gone.
Where'd the water go?
So it's actually not a magic trick. Surprise, surprise. It's actually some hydrogen bonding happening inside this wonderful container here. All things that you're going to get to learn about this first year here at ASU in your Gen Chem classes. Okay. And that's us. Yeah.
All right, next, President's Professor Ian Gould will have a little fun with chemistry color magic.
Good afternoon, everybody. This is participatory. Come on, good afternoon. Okay, so Chad said earlier that you're going to learn chemistry and biochemistry, and he also used the word, I was a little surprised to hear it, but he's right. It's going to be hard work. I mean, learning is, by definition is hard. Anything worthwhile is hard work, right? But we're not going to work hard today. We're going to do some chemistry today, so do some chemical reactions. There won't be a test, right? And you need to help me by paying attention and trying to just, let's find out, just watch some chemical reactions occur, and then we might talk about it a little bit at the end. Let's just see how it goes, right? So I'm going to do something, and you're going to watch carefully. Yeah, you're going to watch carefully. Okay, where are we? So, chemicals, right? Are you impressed yet? Don't be impressed yet. Should we add some more? Yeah. Are you impressed yet? Yeah. A little bit more, right? Right, a little bit more, right? Did anybody see the chemical reaction yet? Yeah. It's okay. Don't be shy. Right, now you're impressed, right? It's a rainbow. Did you notice? What you just saw were acids reacting with bases. You all knew that, right? Yeah. Does an acid react with a base? Everybody's participatory. Does an acid react with a base? Yes. Why does an acid react with a base?
Electrons.
What about the electrons?
Different.
Different what, sorry? potential of hydrogen, that's a different way of saying it. Neutralization, that's the same way of saying an acid. That's the same, basically saying an acid reacts with a base, right? Why does an acid react with a base? Do you think that's fundamentally important?
Yes.
Is it fundamentally important? Yes. Are you going to learn about this semester?
Yes.
Thank you, you will. Enjoy your semester.
Thank you.
That was fun and exciting. Next, instructor Clem will give us a visual demonstration of some ideal gas laws.
Good afternoon. Good afternoon. I have a tradition when I begin a demonstration. I start out by saying, "Hey, class," and then all of you respond enthusiastically with, "Hey, Jim." Ready? Yeah. Hey, class! Today, we are going to look at the gas laws. Now, the gas laws were developed over a period of about 200 years in Europe. So we're going to meet our first gas law in 1662, when Sir Robert Boyle looked at the relationship between the pressure and volume of a gas. So to illustrate that, I have a piston, which kind of looks like a syringe between two blocks of wood, but we'll call it a piston. So when I decrease the volume of gas inside this piston, what's happening to the pressure? Goes up, exactly. So that is an inverse relationship. As the volume decreases, the pressure increases. Okay, why does the pressure increase? More collisions. Because there's smaller space, the gas particles are colliding more frequently with the container walls. So how can you use this? I'm glad you asked. Some of you may have a Boyle's Law apparatus. Ooh, there we go. So again, when you decrease the volume, the pressure increases. But then you let it come out this little tube, pump up your bike tires, and you make it to class on time, which we support. So now let's go from 1662 in England to France in the early 1700s. And to do that, I need a little bit of liquid nitrogen. So liquid nitrogen is about negative 300 degrees Fahrenheit. Just pour that in there. Now, our next gas law was studied by Guillaume Amanton in the early 1700s. And in the early 1700s, the instrumentation wasn't that great. So his relationship between the temperature and pressure of a gas was more qualitative. About 100 years later, Joseph-Louis Gay-Lussac looked at the same relationship, but with better instrumentation. So sometimes this is referred to as Amanton's law, sometimes the Gay-Lussac law. But either way, it's still the relationship between the pressure and temperature of a gas. So to look at that, I have this device here, which has a fixed volume. So the volume won't change. This is sealed up. The number of moles of gas will not change. So we can put it in here, and right now it's just about 15 pounds per square inch. And as I immerse it into the liquid nitrogen, the gas inside is cooling off. So those gas molecules are moving more slowly. They're hitting the container walls less frequently and with less force, thereby reducing the pressure. Is the pressure going down? Okay, yeah, because I can't see through the back. All right, yeah, so down below 10. Now what happens when we increase the temperature? All right. So we've got some good old fire here. Now those gas molecules getting hotter, more kinetic energy, hitting more frequently, more often, and the pressure goes up. Is the pressure going up? All right, good. Right about where we started. Cool. So that takes us into the 1700s. We go to about 1787, when a French scientist, Jacques Charel, looked at the relationship between the temperature and volume of a gas. And here in the US, we call this Charles' law. And in the late 1700s, he used a hydrogen balloon to carry himself aloft about 1,800 feet. So pretty brave, or maybe dumb, you know. But in his honor, I have a hydrogen balloon, and you just saw hydrogen balloons float. So I'm putting it into the liquid nitrogen. Now, is the number of moles of gas changing? No. Okay. Is the pressure changing? Actually, no. This is an open container under 1 atmosphere of pressure. So the pressure is not changing. So it's maintaining 1 atmosphere of pressure. Now, those gas molecules are moving again more slowly, so they're not putting as much outward force on, but they're maintaining 1 atmosphere of pressure in equilibrium with the atmosphere. Do hydrogen balloons float? Ooh. No, they don't. Now, as it heats up, the gas expands, the volume increases, density decreases, and voila, goes higher. All right, next, we are going to go to the early 1800s, and you may have heard of Avogadro's law. So, Lorenzo Avogadro looked at the relationship between the number of moles and volume of a gas. So, ASU's #1 in innovation, I have here a special elastic container, and right before your very eyes, I will increase the number of moles of gas. Here we go. All right, so as the number of moles of gas increased, what happened to the volume? Increased, right? Was that kind of obvious? Yeah. And I'm sure Avogadro's friends thought the same thing. They probably said to him, well, duh, Lorenzo Romano Amedeo Carlo Avogadro. That's obvious. But what's not so obvious is that when you have equal volumes, independent of what the gas is, you have the same number of moles of gas. Right? So what's in this balloon? Hydrogen. Hydrogen. What's in this balloon? Air. Okay, Jim's morning breath, right? So carbon dioxide, you've got some water vapor, mostly nitrogen from the air, and quite a bit of vodka. So, what Avogadro was able to determine is when you have 1 mole of a gas at standard temperature and pressure, it occupies a volume of 22.4 liters, the volume of this box, independent of what the gas is. And then one final thing, since I happen to have a balloon with Jim's morning breath in it. This is like really cool. Probably going to be the highlight of your time here at ASU, so I apologize. It's all downhill from here. Now, when I put the hydrogen balloon into the liquid nitrogen, it remained a gas. It didn't get cold enough to turn it into a liquid. But that's not true with Jim's morning breath. It has stronger attractive forces between the molecules. And right there, you have liquefied Jim's morning breath. What could be better? Would you like to take a drink? No? All right. Fine. You. All right, so there we have the gas laws. Thank you very much.
All right, that was a lot of fun. I'm enjoying this. I haven't actually been to this before, believe it or not. This is a lot of fun. All right, so next we have our ASU's 2 co-presidents of SACS, which is the Students Associates of the American Chemical Society. We have Lauren Harstead and Jesus Peralta. Welcome. They are going to demonstrate an experiment simply known as elephant's toothpaste.
Yeah, so hi everyone, I'm Lauren.
Hi everyone, I'm Jesus.
And, thank you.
Thank you.
So if you didn't catch that, Lauren, Jesus.
Yeah.
And like was said, we are the co-presidents of the student affiliates of the American Chemical Society. So we really are a club within SMS for chemistry and biochemistry students, where you can come and meet a bunch of your fellow classmates. And also we're really into like professional development. So whether you want to go to med school or grad school or get a job right after this, like we're kind of here for whatever you need and connecting you with opportunities within SMS.
All right. Are you guys ready for the elephant's toothpaste now?
Of course.
All right, awesome. So we'll get started with this graduated cylinder. And we're gonna pour some hydrogen peroxide first. If I can open it, there we go.
And to the hydrogen peroxide, we're gonna add just some standard dish soap. We'll switch that up a little bit.
And now to that, we're gonna add some color. Make sure it's dark blue there.
And then our final reagent, some potassium iodide. Ready?
Yeah. Ooh.
And so if you guys are interested in joining our club or learning more about us, you can find us on Sun Devil Sync, which is ASU's website for all of its organizations. And
Yeah, and our first meeting will be August 29th at 5:30. Feel free to join us.
All right. You want to bring a toothbrush? Want to try it out? No, you probably wouldn't. Don't do that. That's not actually something you want to put in your mouth. All right. So for our next demonstration, we have instructor Tim Lamb, who is going to have some more fun with hydrogen balloons. We got a little taste with Clem and Jim, Clem as he's sometimes called. So Tim, take it away.
Okay, hi everybody, I'm Tim Lamb. Those of you taking Chem 117 will probably see me a lot this semester. I'm one of the instructors for the recitations and the labs and all of that. I get to play with hydrogen, which is pretty awesome. So hydrogen is the first element on the periodic table. You can actually see it up there. Atomic number is 1, meaning it consists of just 1 proton and 1 electron. It's pretty simple. There's not really a whole lot going on there. And we typically think of it as being a very dangerous element. If you remember the Hindenburg back in the 30s, oh, the humanity, all of that, it exploded. That was a dirigible or blimp filled with hydrogen, and we know it as a very flammable gas. So that's what I'm going to do today, not blow up a blimp, but blow up some smaller hydrogen balloons. So hydrogen was first discovered in the 1760s, right around there. Initially it was made by people pouring acid on metals, and they saw that it bubbled up, but they didn't really know what was going on with it. Then later on, Henry Cavendish separated it as an individual element, identified it as something that when burned produces water. So these balloons are filled with hydrogen, and if I were to pop one, it would mix with the oxygen in the air, and nothing really would happen, right? Hydrogen, we know that it's flammable, but if we mix it with air, nothing actually happens. It doesn't react with the oxygen to form water. So we need to give it a little bit of extra push, and that's what I'm gonna do with this thing here. We call this a fire stick, as you can see why. I'm going to light it on fire. So if I take the hydrogen balloon and add a little bit of extra energy, we'll talk about this in your classes this semester, there's a little hill that it has to go over in order to actually react. So if I take some fire, okay, This is my favorite demo. I like playing with fire. All right. So take a little bit of extra energy. Yes, it is loud, so you might want to cover your ears. Is this in camera? There we go. So take a little small flame, put it to the balloon. Woo. Get an awesome explosion. Thank you. You want to see that again? Yeah. And another 3 or 4 more times? Yeah, we'll do that. So, let me grab another balloon here, relight the stick, and have another boom. Oop, there we go. Come on. Here we go. Try to make sure this is visible. 3, 2, 1. Yeah. Also, I should mention this is a very exothermic reaction. It releases a lot of energy, so those of you standing or sitting in the first couple of rows might feel a little bit of heat coming off of that. But no water, so it's not raining and blowing up a bunch of hydrogen balloons. That's because there's so much energy that it's being produced as water vapor and not actually raining down on us. Although my goggles are fogging up, but that's a different story. All right, here's another one. I got one more big one here. Woo, that was a good one. Ow. I think I actually got a little bit of a spark on my neck. I'm okay. I've done this plenty of times. Maybe I won't do it so close to my head. All right, last one. Here we go. This one's got a nice smiley face on it. So let's see what happens. Last one. Woo. All right. Woo. That is the hydrogen balloon. Thank you very much.
All right, next lecturer, Dr. Ashley Morgan, will continue some fun with fire.
Hi, everyone. Hi. And online. All right. Oh, I'm not disappearing. Okay. So, I don't know if I can bring the heat like Tim can, but I'm going to attempt to be exciting, okay? So I'm going to need some more fire. As you'll notice, we like to keep it hot here, right? Not just outside. All right, so what we find in a lot of our chemistry courses is that whenever we're looking at things like the flammability of hydrogen or a lot of the chemical reactions, what it really comes down to are electrons. How electrons are arranged, how they move, and that is what kind of we want to dig into. We want to go from this macroscopic understanding of chemistry in the world around us to a more microscopic one, and what better way to do that than with a demo. So I'm going to do today a flame test. Has anyone ever seen a flame test? Have you ever seen fireworks? If you've seen fireworks, you've seen basically a flame test. So what's really interesting is that when electrons are excited, see, I told you I'd keep it exciting. When electrons are excited to higher energy levels and they fall back down, they begin to emit energy, right? And sometimes this energy is in light that we can actually see. So sometimes it's outside of the realm of the visible spectrum, but today I brought with me 5 examples of some metal salts that whenever we excite them with the fire, we're going to see some characteristic colors. These colors come from the very specific ways that their electrons move, and it's actually one of the ways that we begin to discover or identify what maybe a substance is made of. All right, so I'm going to kind of do these in order of my least favorite to my favorite. All right, okay. Mood set? Okay, here we go. So first one, I have some sodium chloride and methanol. The methanol is just to give us kind of a little bit more pizzazz, all right? But really what we're going to see is looking at the effect of the electrons moving in the sodium ions themselves, in sodium. So whenever we take a look at that, what color did you see? Orange. So this, I think, for most students is kind of meh. For me, it's kind of meh because it looks like fire, right? Just nothing too exciting. All right, so then we have some calcium chloride. Let's look at what calcium looks like. And once again, their electrons are different. There's different arrangements. Whenever they're excited and they come back down, they do so in different patterns, and that's why we see different colors. So it's kind of like an orangey red, starting to get exciting, right? Then we have some strontium chlorides. Looking at some strontium metal here. Very nice, right? Very nice. Okay. Now we're getting into my two favorite. This is honestly a tie because I really can't decide. Some days it's one, some days it's the other. My favorite color? Right? This would make a great nail color. Yes. All right, so we've got this nice lavender color, and this is coming from the potassium. But in all honesty, most students really love this one. This kind of is a winner, all right? Right? You have to keep Halloween, it's coming, right? All the decorations are already out in the stores. But, you know, we can't just look at this by themselves, right? You guys are here for your Sun Devil welcome, right? Go Devils. Thank you.
All right, thank you, Dr. Morgan. So for our grand finale this afternoon, Jim is going to show us what happens when you mix together a really hot liquid with a really cold liquid.
Hey, class! Today, we are going to look at the strength of intermolecular forces. Now, I just introduced intermolecular forces to you with Jim's morning breath, liquefied. But here, I'm going to use, as you just heard, something really hot and something really cold. So right here is some hot water, something I'm usually in. Now here, I've got our friend liquid nitrogen again. Oh, whoops.
That's why you wear long pants, by the way, in lab.
There we go. All right.
I'm going to move over here.
Chicken. So here we've got our liquid nitrogen at negative 300 degrees Fahrenheit. And you can see it's boiling away. Now, what are the intermolecular forces holding those nitrogen molecules together? Well, in this case, call them London forces. You'll learn about these later on. And they're based on the molecule's mass. So we've got nitrogen, N2. If we look up on the periodic table, nitrogen's atomic mass is 14. 14 times 2 is 28. Good. Got some math scholars here. All right. So there is our liquid nitrogen. Now let's compare that to water, dihydrogen monoxide. Okay, it also has London forces. What is the molecular mass of water, H2O? 18, that's good. Each hydrogen's 1, and then oxygen is 16 for a total of 18. So which of these two has stronger London forces? Okay, the heavier one, the more massive one. Right? But how come the water is nearly 500 degrees Fahrenheit hotter in order to get it to boil? Well, it has some other attractive forces holding those molecules together, and we call those hydrogen bonds. And you can see the strength of the hydrogen bonds even though water has a lower molecular weight. It takes a lot more energy to pull apart those water molecules to go from a liquid to a gas. Right, now, how often do you have two liquids next to each other that have about a 500 degree temperature difference? Didn't do that this summer? No? All right, how would you like to see me combine them? All right, all right. You ready? Here we go. I'm going to take some of the water. They seem underwhelmed. Maybe I'll add a little bit more water to it. Ooh. Could you see that in the back?
No.
All right. Have you been to SeaWorld?
I want to sit in the front, honestly.
Yeah, you might want to move. Okay. Yep, let me come back that way. Thank you. You really might want to move. Because I'm going right there. the expression, go big or go home? Yes. Yeah, that's what we're doing today. So I happen to have a little bit more liquid nitrogen, a little bit more water, bigger container. Ooh. So before I mix these, let me explain what happens, why you saw a cloud. Okay, so you've got the liquid nitrogen in there, and then when I put in the water, the hot water, it turns the liquid nitrogen from a liquid to a gas, making it expand very rapidly. And when it expands, it shreds apart the water molecules into tiny little droplets, which forms a cloud, which is why we call this the cloud demo. So here we go. Put in my liquid nitrogen. And you might want to grab your phones and record this. Let me move that out a little bit. You may have heard a redneck's last words. Hey y'all, watch this. All right, could I have a countdown from 5, please? 5, 4, 3, 2, 1. And there we have intermolecular forces.
All right, we hope you have enjoyed these demonstrations, maybe learned a little something along the way. I can't guarantee you that the lab experiments that you do will be quite this fun, certainly not as dangerous. We try to stay away from danger in the labs, but hopefully this has at least whet your appetite for things to come in your chemistry careers here at ASU. So we thank you for attending and for your participation and attention. We hope you have a good afternoon.